My second talk today is about the Hubbard U parameters and how they can be calculated from first principles using a method called constrained random phase approximation. Why would you be interested in it? Well, if you're interested in strongly correlated materials, these are materials which have partially filled d orbitals or partially filled f orbitals, then the electron correlation is often so strong that DFT or GW might not be sufficient, and you might have to use a different set of approaches that are based on the Hubbard model. For example, Hubbard 1, LDA plus DMFT, LDA plus Gutzwiller. LDA plus U is more like a hybrid between the two worlds. In this context, one often talks about this ratio as a measure for the correlation strength. The Hubbard U parameter divided by the bandwidth. If this ratio is small, for example for alkali metals or transition metals, then DFT or GW will still give you a pretty good description of the electronic structure. On the other hand, if the ratio is large, as is the case for transition metal oxides or rare earths, then you might have to use a more model-oriented approach. How can we understand this approach? I want to start out with something that you all know very well: the many-electron Schrödinger equation, with the kinetic energy, the potential energy, and the electron-electron interaction energy. As you all know, the many-electron Schrödinger equation cannot be solved exactly, and we have to resort to approximations. There might be two strategies of doing that. The first is to approximate the Hamiltonian, and then you have approaches like Hartree-Fock, density functional theory, GW, and so on. In the other strategy, one tries to keep as much of the physics that is contained in the Hamiltonian as possible, but one allows for a reduction of the system. This is done by a partitioning of the system into a correlated subspace, for which one constructs a quantum mechanical Hubbard model, and the rest. The correlated subspace might consist of only the localized D states or F states. Such a partitioning of the system is called downfolding the Hamiltonian, and then you have methods like LDA plus U, LDA plus DMFT, LDA plus Gutzwiller, Hubbard 1, and so on. This is the many-body Schrödinger equation in the familiar form of the so-called first quantization. We can write the same equation in a form that looks completely different, but it is exactly the same thing. It's called second quantization. Somehow it looks more complicated than the first equation. However, we have some formal simplifications here. In the first line, we have a number of very different operators: kinetic operator, single particle potential operator, and the two-particle Coulomb operator. In second quantization, on the other hand, we only have two different operators: an annihilation operator, C, and a creation operator, C dagger. They remove a particle from the many-body system or add a particle to the many-body system. There is a simple mathematical definition of how these operators act on Slater determinant. The matrix elements of second quantization are just complex numbers. They are the matrix representations of the operators that we see explicitly in first quantization. So they are mathematically uniquely defined. Still, we have not really gained so much from this reformulation. What we still have to do is downfolding the Hamiltonian, for example to the extent that we limit the system to a single band, which gives the one-band Hubbard model. We have three terms in the Hamiltonian: the hopping term that contains only nearest neighbor hopping, the on-site term, and the electron-electron interaction term, which derives from this part. The middle term only affects the energy zero and can be eliminated. And then we are left with only two terms, the hopping parameter and the Hubbard U parameter. Since we can divide the whole equation by t, there is only one independent parameter, and that is the ratio U divided by t, the measure for the correlation strength, which we have already encountered before. Now, what is the Hubbard U parameter? Is it one of those matrix elements, or is it an average over them? No, that's not so, because we should not forget the rest of the system. We have separated the Hilbert space into the correlated subspace and the rest. And the rest also contains electrons, and these electrons take part in the screening of the electron-electron interaction. Whenever two electrons in the correlated subspace interact with each other, they do not do so with a bare Coulomb interaction, but with an effective interaction that incorporates the screening processes of all other electrons that are not included in the model subspace. So the Hubbard U parameter contains a lot of the complexity of the full many-body problem. Whereas the hopping parameters are relatively straightforward to calculate, it is the Hubbard U parameter that makes things more complicated. And this talk is about calculating the Hubbard U parameter from first principles. Let's have a look at an example for the partitioning of the Hilbert space. This is strontium vanadate, which is the nice feature that the T2G bands form an isolated set of bands around the Fermi energy. That is, they do not overlap with any other band. It appears quite natural to take the T2G orbitals to define the correlated subspace. The other electrons are in the rest space, which we call R space here, and the correlated subspace is called L space. For the R space, we would use, for example, DFT, and for the L space, we would use the Hubbard model. In practice, there are two main ab initio approaches for calculating the Hubbard U parameter. The first is the constrained local density approximation. Here, the Hubbard U parameter is defined as the second derivative of the total energy with respect to the occupation number of, for example, the D shell. From this, you have to subtract a hybridization term. The advantages of this approach are: it is quite straightforward to implement in a DFT code, and computations are fast, because it is DFT. But the information that you get is limited. For example, the frequency dependence is not accessible, and you cannot get individual matrix elements, such as the Hund's exchange parameter or off-site Hubbard U parameters. On the other hand, the constrained random phase approximation is not subject to these restrictions. However, it is generally computationally more expensive. Anyway, if you are interested, you have a chance to calculate Hubbard U parameters in the afternoon hands-on session. What is the idea of constrained random phase approximation? Let us consider the polarization function, which we have already encountered in the talk about the GW approximation. It contains a double summation over occupied and unoccupied states, so it can be understood as a summation over all single particle excitations, which go from below the Fermi energy to above the Fermi energy. Now we can classify these excitations into excitations that take place in the correlated subspace, like the red one, and the ones that somehow involve other bands outside the correlated subspace. For example, going from the rest space into the rest space, or from the correlated subspace into the rest space, and so on. By this classification, we can write the polarization function as a sum of two terms, the PL, which contains the red excitations, and the PR, which contains all the green excitations. The PR then describes the screening processes of the electrons outside the correlated subspace. We want to eliminate the PL because the screening of the electrons in the correlated subspace is supposed to be treated within the Hubbard model. In other words, if we did not eliminate PL, we would have double counting of screening processes. The partially screened Coulomb interaction is then obtained by renormalizing the Baire interaction, V, by the polarization function, but only by the polarization contribution from the rest of the system, PR. Then, in order to finally get the Hubbard U parameters, we have to project the partially screened interaction onto a basis of Wannier functions. What Wannier functions are, you have already learned in the talk by Dongwook Go. In this way, we get the effective local interaction parameters with all the advantages of constrained random phase approximation that I have already mentioned before. I want to talk briefly about the case of entangled bands. In other words, what happens if the bands are not so nicely isolated as in the example of strontium vanadate? For example, in nickel, the D bands are entangled with the S band, which makes it impossible to classify the excitations uniquely. There are two approaches to tackle that problem. The first is our own. I called it projection method. Here we scale each virtual excitation by a prefactor Pm times Pm prime. Pm is the probability that an electron in the state M is in the correlated subspace at the same time. The probability is obviously between 0 and 1 and can be calculated by projecting the state M into the space spanned by the Wannier functions. We do the same thing with the state that the electron goes into. This gives Pm prime. And the product of the two numbers is again between 0 and 1. There is another method which was proposed 2 years before ours by Takashi Miyake and co-workers. They argued that the problem is caused by the hybridization between the subspace and the rest. This hybridization is simply eliminated, which immediately disentangles all the states, and we can use the first equation again. Both methods are implemented. We usually use the first method because it is a bit more straightforward. Finally, we do not only get a single number, as the term Hubbard U parameter might suggest, but a whole matrix. And it is a rather big matrix, because, forgetting the frequency and spin dependence, it has 4 orbital indices. For a D shell, this would give 5 to the power of 4, that is 625 different matrix elements. Here, each m stands for a magnetic quantum number. Spex writes the non-zero matrix elements to a file, spex.q. Luckily, this complexity can be reduced if one assumes, first, that the screened interaction is isotropic, and second, that the radial Coulomb-Slater integrals are independent of the magnetic quantum numbers. Then only 15 out of the 625 elements are different. And only 8 matrix elements will be different with another simplification of the Hamiltonian, often made in DMFT calculations, where one expresses the electron-electron interaction only in terms of density operators. Of these 15 or 8 different matrix elements, only 3 are independent, and the others can be constructed from these 3. The 3 independent parameters are given at the end of the standard output of the Spex code. We have seen that, in the case of strontium vanadate, the correlated subspace was composed of T2G orbitals instead of the full D shell. Indeed, this further reduces the number of different matrix elements to 3, or only 2 independent ones. The same holds for a correlated subspace that is formed by EG orbitals. Again, the 2 independent parameters are written at the end of the standard output of Spex. As an example, we show Hubbard U parameters that we have calculated for the 3D transition metals from scandium to copper. In red, we see the Hubbard U parameters, in blue, the corresponding fully screened parameters. The latter also contain the screening happening in the correlated subspace, which is why they are significantly smaller. On the right-hand side, we also plot the respective Hund exchange parameters. As you know, some of the materials are ferromagnetic: iron, cobalt, and nickel. Also, manganese is ferromagnetic in the structure we have calculated it, a high-temperature phase, with 1 atom per unit cell. There is a criterion for ferromagnetism that can be derived using the Hartree-Fock approximation for the one-band Hubbard model. This so-called Stoner criterion states that if the product of Stoner parameter I and density of states n at the Fermi energy is larger than 1, one would expect the system to be ferromagnetic. For the Stoner parameter I, there is a formula published by Stolhoff et al., which gives I as a function of U and J. In fact, if we use the calculated U and J parameters and evaluate the left-hand side of the Stoner criterion, we find it to be fulfilled for the materials that are known to be ferromagnetic: manganese in the high-temperature phase, iron, cobalt, and nickel. As another example, we consider the Hubbard U parameter at surfaces. What would one expect? You would expect that the screening is smaller because you cut away half of the system, and hence you have less electrons in the surrounding that can screen the interaction. Less screening means higher U parameter. In fact, this is the case for aluminum and also for sodium chloride. The U parameter is large at the surface and gets smaller for the layer below and even smaller for the next layer, and so on, until it reaches the bulk value. However, this qualitative behavior is not a general rule. For example, for BCC chromium, we see the opposite behavior. The Hubbard U parameter at the surface is smaller than the bulk value. This is caused by the presence of surface states that, in the case of the 100 surface termination, even produces a peak in the density of states where the bulk shows a minimum. These surface states are metallic and contribute significantly to the screening. So even though there are less electrons, the ones that are there can very efficiently screen the interaction. And this is why the surface Hubbard U parameter is smaller than the bulk parameter. At the end, I want to say a few words about how a calculation of the Hubbard U parameter is carried out in practice. Just to remind you, this is the procedure for the one-shot GW calculation with the corresponding job definition. For a Hubbard U calculation, not much changes. Of course, you have to change the job definition, and you have to define a Wannier basis for the correlated subspace. The rest is done by the specs code. If maximally localized Wannier functions are requested, specs calls the Wannier 90 library. The elimination of the subspace polarization and the projection of the interaction onto the Wannier basis is all done automatically. To summarize, for strongly correlated systems, methods like LDA plus U or LDA plus DMFT, which are based on the Hubbard model in a correlated subspace, might be more appropriate than density functional theory or GW. These methods require an effective interaction parameter, the Hubbard U parameter, which incorporates the screening processes of the electrons that are outside the correlated subspace. The constrained random phase approximation is a first principles method to determine the Hubbard U parameter. Specs has an implementation of CRPA. The correlated subspace is spanned in a Wannier basis, and we have a possibility of treating entangled bands.